Okay, so we've been away for a while, and I just wanted to complete this chapter 11. We're going to look at particle conservation numbers, particle conservation laws. And before going forward, it's important to understand in physics that whenever we have a symmetry, and this is what's called Noether's theorem, whenever we have a symmetry, we can have a conservation associated with that symmetry. Now, this is not a geometrical symmetry the way that we normally think about symmetries. This is a symmetry where if we do some type of transformation, certain aspects of nature remain unchanged. And I'm oversimplifying this. I wish I could express this in a more elegant way, but it's really by seeing these symmetries and then finding out what is conserved, we can sort of predict the outcome of different type of particle interactions. I guess that's really the best way and the simplest way that I can put it at this point. Now, let's think about some of the symmetries and the conservations that we have in classical physics. So for instance, we know that there is translational symmetry. Basically, you can move in the x, y, and z direction, and the laws of physics will pretty much remain the same. This leads to our conservation of momentum. You notice that we have three different dimensions that are spatial, and thus we have three different conservations of momentum. That is, we have conservation in the x direction, conservation in the y direction, conservation in the z direction, if we want to use that coordinate system. Rotational symmetry also leads to its own conservation of angular momentum. Temporal symmetry, basically our symmetry in time, in fact, leads to conservation of energy. So again, we can predict how different things will behave in nature based on these different symmetries. And essentially, if we look at a mechanics problem and we say, well, we know momentum is going to be conserved, we know energy is going to be conserved, we can predict the outcome. So we have four basic conservation laws that we're probably aware of already: conservation of momentum, conservation of angular momentum, conservation of energy. I'm going to throw a fourth in here. That's conservation of electric charge. And that's a little bit more difficult to explain. That has to do with the symmetry that's associated with the electric field. And, basically, if we express the electric field, we can use complex numbers to associate the phase of the field at any one time. I wish I were explaining this a little bit better. But the fact that we can, actually, advance this phase at any point, actually, it's associated with a gauge theory. So I've got to be a little bit careful here. But effectively, electric charge is going to be conserved, and this is very much associated with the symmetries in the electromagnetic field. I'll leave it at that. Particle physics provides us with additional conservation laws or conservation numbers where we can say, okay, these are the numbers that we start out with. Our expectation is that these values will be conserved. And there are also some exceptions to the rule where they're not always conserved. Now, these numbers include baryon number, lepton number. In fact, inside the lepton number, we sometimes will see conservation of the electron lepton number, the muon lepton number, and the tau lepton number. But the neutrino gives us sort of a interesting breaking of the symmetry, and the fact that neutrinos oscillate mean that these numbers are not always conserved. In addition to baryon and lepton number, there's also a strangeness number, and this was sort of important at the beginning of the discovery of the quark. And then finally, the quarks have their own type of charge. And this is not electrical charge the way that we think about electrical charge. We know that opposite electrical charges are attracted to one another, we find that in quarks, there is actually an attraction due to a strong type of charge. These are not physically red, green, and blue, but we associate red, green, and blue with them because instead of two charges, positive and negative, we actually have three charges when combined. Instead of neutralizing into a zero charge, I guess you could sort of say they neutralize into a zero charge. In this case, what happens is that when we combine red, green, and blue, we get white, and that's considered sort of the neutral state of this. Color charge is a little bit complicated because it can almost be thought of as a three-dimensional vector where it points in the red, green, or blue direction. Again, they have nothing to do with the true colors that we see. These are just the different amounts of this charge associated with the strong force. Okay, let's start with baryon number. And what was observed early on was if we do some type of reaction, we'll call it a reaction, although it's not a reaction in the chemical sense, we have particles that interact at the beginning, and after the interaction, we have different products. When we look at these reactions, we say that the baryon number, in most cases, is going to be conserved. Now, for instance, a proton is a baryon, a neutron is a baryon. They both have baryon numbers of 1. And in many of these particle conservation numbers, the antiparticle has the opposite of the particle in terms of the number. So a baryon, such as a proton, would have a baryon number of 1. An anti-baryon, such as its antiproton, will have a baryon number of -1. So before and after these types of interactions, our expectation is that this number is going to be conserved. If we look at, again, different particles, photons are not baryons, so they don't have a baryon number, or the baryon number would be considered to be 0. Electrons or leptons, they are not baryons. They have a baryon number of 0. But again, proton, baryon number of 1. Antiproton, baryon number of -1. Pions are not baryons. They are mesons, so their baryon numbers are also 0. And then you have more exotic baryons, which exist at higher energy levels, such as a lambda naught, sigma particles, chi particles, and of course, omega particles with values of 1. So let's look at the decay of a neutron. We talked about this as being related to or mediated by the weak force. And of course, if a neutron is left on its own, it has a half-life, it will decay into a proton. But it will also produce both an electron to conserve charge, so we've got to conserve that number right there, and an anti-neutrino, which we'll talk about in a little bit. So looking at the baryon number, the neutron has a baryon number of 1, so after the reaction, we produce a proton, which has a baryon number of 1 also. One might think that a neutron could decay if this were energy allowed, but it's not, into a proton and an antiproton, because that would conserve charge. But in that particular case, we'd go from a baryon number to 1 to a baryon number of 0, because a proton plus an antiproton, of course, would be a net of 0. But again, we can see again, this type of interaction is allowed as far as the conservation of baryon number. What about the annihilation of a proton? What if a proton comes up with its anti-matter particle? Well, in this case, this again is allowed. We conserve baryon number. We have a baryon number of 1 for our proton, a baryon number of -1 for our antiproton. So when they annihilate, they simply produce a gamma ray. Gamma ray is not a baryon. It has a baryon number of 0. So before the reaction, our baryon number is 0. After the reaction, our baryon number is 0. Pretty much the same thing that we do with chemical reactions. when we look at chemical reactions, we want to make sure that the reactants on one side are equal to the products on the other side. Here we want to make sure the baryon number on the left-hand side of this reaction is equal to the baryon number on the right-hand side. It's also possible that if we come in with enough energy that we could have a reaction that produces more particles. This is actually allowed. We could actually have a proton and an antiproton come in and produce more proton-antiproton pairs. This is a little bit more difficult to have happen, but it's allowed. We know that if there's enough kinetic energy here, that kinetic energy can be converted into more matter. In fact, we can imagine this is the type of reaction that could take place in a particle accelerator. And of course, the result here is we not only have a proton and an antiproton leaving the reaction, we might have an additional pair, which is allowed. And again, this completely conserves our baryon number. We come in with 0, particle, antiparticle, particle, antiparticle, 1 plus -1, 1 plus -1, we still equal 0. That type of interaction would be allowed. We could even come up with more exotic particles. Let's say we slam a proton and an antiproton into one another at even higher energies. This is one way we could look back in time and find baryons which are not common. We could discover more massive particles like the lambda particle and its antiparticle, the omega particle and its antiparticle. Again, in the input into this system, we have a baryon number of 0. As long as we have a baryon number of 0 at the end, we would be fine. In fact, we could slam 2 protons together, and as long as the baryon number after they collide with one another, this is something that you have happen at the Large Hadron Collider. You slam two protons at very high speeds, you could produce a lot of particle antiparticle products from this, and again, see particles that are not common during this point in time. But as long as your baryon number at the end equals what it was at the beginning, you would be fine with producing this. So again, looking at baryon numbers, in most cases, baryon number is conserved. I know that there are a few odd exceptions to the rule, but it's based on a symmetry, and as long as that symmetry isn't broken, which it isn't in most cases, almost all cases, we can have an expectation of what we will see coming out when we collide particles compared to what we put in. Now, lepton conservation, as I sort of gave a prelude earlier on, lepton conservation is a little bit tricky because of the neutrino. And if we look at this, electron is a matter particle, so it has a lepton number of 1. Its antimatter particle would therefore have a lepton number of -1. But in addition to just straight lepton particle number, okay, there's also a lepton number associated only with the electron. So this number here, the electron lepton number, is 1 for the electron and the electron neutrino, and -1 for the positron and the electron anti-neutrino. Of course, we have the heavier cousin to the electron, the muon, okay? And the muon has a lepton number of 1, but it also has a muon lepton number, a mu lepton number of 1. Its antiparticle, -1, okay? And even go up to the tau or the tauon, that has its own number associated with it. A tauon would have a lepton number of 1, but also a lepton tau number of 1. Its electron lepton number would be 0. I hope that's not getting too confusing here. Okay, so again, we can see the different lepton electron numbers, lepton muon numbers, lepton tau numbers, and our expectation is they would be conserved in some type of interaction. All right, so for instance, let's go back to the decay of the neutron. The neutron decays naturally into a proton, but because the neutron is slightly heavier than the proton, we're also going to have some energy converted into mass. That becomes the electron plus the electron neutrino. Now watch what happens here. Our baryon number is 1 at the beginning, our baryon number is 1 at the end. There are no leptons at the beginning, so our electron lepton number is 0. And in order to produce a electron, lepton number 1, electron lepton number also 1, we have to produce an antineutrino. Okay, so that's how we balance that number right there. And when this type of decay was first observed, I believe it was Enrico Fermi. I hope I'm getting this correct. Fermi, looked at the momentum of the particle coming in and the momentum of the particles going out, and he noticed momentum wasn't conserved. Momentum, there's some missing momentum, and he hypothesized that this was some ghost particle that he couldn't detect. And of course, this was the little neutral one, the neutrino, which is very hard to detect because it only interacts through the weak force. So it wasn't until much later that we even were able to confirm the existence of this particle. Again, this conservation number, predicts that it should happen. We should produce an anti-lepton. Gamma rays don't normally produce pairs unless they're able to transfer some of their momentum to another particle like a nucleus. But it's entirely possible that a very high energy gamma ray, when interacting with the nucleus, and all it needs to do is exchange a little momentum there, will transform into a electron-positron pair. Now, this is really one of the easiest ways. Is this one of the easiest ways to generate antimatter? I guess we can generate positrons in beta plus decay, but if you want to manufacture antimatter using very high energy interactions, in this case we're using a gamma ray, we can turn some of the energy into this electron-positron pair. In fact, this gamma ray, we don't have to just stop there. We can, go to even higher energies and produce a proton, antiproton, a neutron, antineutron, and even a heavier baryon than that. But as we can see here, lepton number is 0 on the left-hand side. Gamma rays aren't leptons, so their lepton number is 0. After the interaction, our lepton number is still 0 because the electron has a +1, the positron is a -1. Here the charge is conserved, -1 elementary charge, +1 elementary charge. This type of interaction is allowed. Likewise, positrons readily annihilate with electrons. When that happens, we actually produce 2 gamma rays. And this is very, very important because in PET scans that we use oftentimes to try to detect tumors, the PET scan works by detecting each of the gamma rays, which are normally given off in opposite directions. And by tracing back their location, the PET scan can say where the positron was given off. And usually a radioactive tag, which is usually attached, something, is it technetium? Usually radioactive oxygen, I think, is usually what happens here. But you tag glucose with this positron emitter, you can see where the glucose ends up within the body. And usually tumors, because they're constantly dividing, use a lot of energy, give away their presence from this positron emission. Now, the decay of a muon is interesting here because with the decay of a muon is going to decay into lighter particles, such as the electron. But here you see this muon has a muon lepton number of 1. So when it decays through the emission of this W particle. Of course, the W particle is associated, the W minus particle is associated with the weak force. So we can see this muon comes in, decays into a W minus, and decays into a muon neutrino. So we're conserving the muon lepton number, temporarily. Okay, we're conserving that, and the W particle has no lepton number to it, but that decays into an electron. Okay, electron lepton number of 1, and of course it also produces an antineutrino. But this neutrino and this antineutrino have different flavors, flavors with leptons. I don't know how they came up with all these different things. There's the electron flavor, the muon flavor, and the tauon flavor, the tau flavor. But again, we conserve charge. The muon has a negative charge, the electron has a negative charge. We conserve mu lepton number. It's equal to 1 here, it's equal to 1 here, these are 0. We conserve electron lepton number. This has 1, this one has -1. So again, we can understand, or we can have the expectation that these particles should be produced according to the conservation laws that we understand and the symmetries that we know are associated with these particles. Here's the problem. These conservation numbers were well understood when we started first understanding fusion at the center of the sun. And we understood, when you fuse protons together, you produce deuterium. The deuterium then fuses together. I'm hoping I'm getting this right. Helium-3. I'm thinking about the PP chain. And then the helium-3 fuses together to produce helium-4, plus releases some protons back into the core. So when these fusions take place, the proton and proton fuse together to produce deuterium, but to conserve charge, the deuterium has to release a particle to take away the extra positive charge. So we release a positron. Okay. Problem. Because we're releasing a positron, we also have to release a neutrino. Okay, that helps with our neutrino. I'm sorry, our lepton number, our electron lepton number. But when we look at or actually measure the neutrinos that were coming from the sun, the number of neutrinos that we expected from production of the positron, because the electron neutrino just passes easily through the sun, was much smaller than what we expected for the amount of nuclear fusion we needed to get the sun to produce the amount of energy that it had. Okay, we can look at the sun and we can say there's this much energy coming out, and given that much energy, we should be producing this many neutrinos. But we weren't detecting the number of neutrinos that we should. And the reason for this is the neutrinos that are being created actually oscillate between their flavor. This is more complicated than I'm explaining here, but we can imagine a neutrino being created which has an electron characteristic, but it actually oscillates where the electron characteristic will oscillate, and the muon nature, the muon lepton number. Oh, I hope there are no particle physicists watching this. They would have my head for this. oscillates out of phase with that. So long story short, I guess the easiest way I can explain this is the electron neutrinos that are being created will oscillate in flavor and at some point become a mu neutrino, a muon neutrino, which will pass right through our detectors, which are only designed to detect the electron neutrinos. And that was why we were actually detecting fewer neutrinos than we knew were being created by these reactions. So here's a breaking in the symmetry where this conservation of a certain type of lepton number is not conserved due to this oscillation. Now, what other numbers do we have? It almost seems like we come up with an unlimited number of different numbers. Another type of number which is conserved is strangeness. And this was, really important at the beginning of the discovery of quark. And again, I hope I'm doing this justice. It's hard to go into this stuff in an introductory course, but it was soon discovered that we're smashing particles together, and these particle accelerators producing more and more massive particles with new properties. And one of the new properties that was seen to be conserved was this idea of strangeness. And for instance, looking at certain particles, kaons, lambdas, sigmas, chi's, omegas, would have different amounts of strangenesses associated with them. And these strangenesses were assigned a particular number. Again, these particles were created. They're not particles that exist in our everyday world in large quantities. Most particles that we see together today in terms of elementary particles are protons, neutrons, and electrons. And of course, the neutrinos, which seem to pass through us without any difficulty. But at higher and higher energy collisions, we were starting to see these more exotic particles, these kaons, these lambdas, these sigmas, these chi's, these omegas, which had this extra property that protons and neutrons did not have, which was also conserved. So this strangeness number was conserved. And there was this symmetry that we could arrange these particles in, which actually led to the proposition of a new idea that these particles were not fundamental, that the protons and neutrons, the kaons, all of these things were not neutral and were actually due to even smaller particles that we now know are quarks. So for instance, if we arrange the mesons, we can actually see they come in 3 different charge possibilities. The pion is one of the most common of the mesons that we know. There's a neutral pion, pi naught, or pi 0, a negative pion, positive pion. But for the kaons, they're either positive or neutral. I'm sorry, positive, neutral, or negative. In terms of the kaons with a strangeness of 1, they're either 0 or the kaon plus. For strangeness of -1, we can have the 0 or -1 here. Again, I'm doing a terrible job explaining this. But again, if we arrange them according to charge and strangeness number, they seem to have this symmetry associated with them. We can do the same with the baryons, which are spin 1/2. Of course, we know the neutron and proton as being the most famous of the spin 1/2 baryons. But again, we were generating these more exotic particles, these sigma particles, these lambda particles, which would have different strangenesses, from 0 to -2. And finally, for the spin 3/2, it became even more extreme, that we had charges from -1 for an elementary charge up to +2, and strangeness numbers going all the way to -3. Now, again, this was figured out by people with much greater intellect than my own, but we can understand why we see this the way that these particles are arranged if we understand that they're not fundamental. They're actually made out of these smaller fundamental particles. So, for instance, I know what you're going to say. Well, the neutron is up, down, down, and the proton's up, up, down. Yes, that is true, but the way that the quarks are arranged, you can actually get spin 3 half if they're all oriented in the same direction. Okay, again, not a particle physicist, but the delta knot particle does have the same quarks as our neutron, up, down, down, except for our neutron is spin 1/2 because 2 of the quarks are spin up, 1 of the quarks is spin down. But in any case, if you want to create any of these particles, you just have to arrange out of a possibility of 3 basic quarks, an up quark, a down quark, and a strange quark, which is not found in the protons and the neutrons. So, for instance, for all our strange particles of 0, okay, we are just combining up and down quarks. Up quarks have a charge of 3/2. Down quarks have a charge of -1/3. So if I have got 3 up quarks, you know, 3, did I do this right? Sorry, it's thirds. It's thirds. Told you I'm not a particle physicist. The up quark has a charge of +2/3. Okay, this is going to give me the right number now. This is why we conserve numbers. And the down quark has a charge of -1/3. So stick with me here. 3 up quarks, 3 times 2/3, so 2/3 plus 2/3 plus 2/3, that gives me a charge of 2. Okay, whew, got that. Now I've got 2 up quarks. Charge 2/3 plus charge 2/3 gives me 4/3. Subtract off 1/3 from my down quark, and I have charge of 1. If I have up, down, down, 2/3 for my charge, -1/3, -1/3, that gives me a neutral particle. Okay? And again, you can go on with this and combine the different quarks. Here we have our omega minus particle, which is 3 strange quarks together. Each strange quark has a strangeness of -1. I don't know how they came up with a strange quark has a strangeness of -1. But the strange quark itself has a charge of -1/3. So if I put this all together, a strange plus a strange plus a strange, I get a -1 or 1 negative elementary charge particle. Okay, but basically, looking at these symmetries, led the particle physicists at the time, Murray Gell-Mann, of course, is credited with coming up with that's the last name, by the way, is credited with coming up with the idea of the quark, because he saw in here a symmetry which is conserved in these particles, which this threefold symmetry led him to believe that there are 3 different quarks in nature. The reason why we didn't include the charm, the top and the bottom quark, is that they weren't produced at the energies which were observed in these particle interactions. That basically they were only creating up to particles with strange quarks. We needed higher energies to get even further. So again, we do have conserved quantities in nature, and I so superficially covered the particles here, you know, in a much higher level course, you would go into these conservation numbers and how, when symmetry is broken, these conservation numbers don't hold. But it allows us to say, all right, I'm going to interact these particles in, let's say, a particle accelerator. What is allowed? You know, what particles do we expect coming out of the reaction? And if I don't observe a particular particle, or there's something missing there, I can go back and use the conservation numbers to sort of, you know, recreate what happened during the interaction. It's very much like this. You know, after an automobile accident, they will do, you know, a forensic analysis of, you know, where the tire marks were, how much energy was involved in the distortion of the different vehicles. They'll basically use conservation of momentum and conservation of energy to sort of say what exactly happened to the vehicles right before a particular collision took place. Okay, that's pretty much what they have in these particle accelerators. They'll use different conservation numbers to try to see what exactly happened, what was produced, especially in the case where you have these very, very high energy particles that are produced. Higher energy typically means that they're going to have a shorter decay life. So again, that's our conservation numbers that we see in particle physics.